Dear students, Assalamu alaikum. This lecture video is the continuation of my previous lecture video on heterocyclic compounds. In this lecture video, I shall discuss about two more heterocyclic compounds, that is pyridine and quinoline. At first, I shall discuss about pyridine. Pyridine is a six-member heterocyclic compound. Here, the heteroatom is nitrogen. We can see the structure of pyridine here. Actually, its structure is similar with benzene. Pyridine replaces one of the CH of benzene by a nitrogen atom. Pyridine is an aromatic compound. The lone pair electron on nitrogen is present in an sp2 hybrid orbital, which is perpendicular to the p orbital. That's why this lone pair electron is not involved in the delocalization of pi electron. Pyridine follow the basic four criteria for aromaticity. That is, the compound is cyclic, planar, completely conjugated, and follow the Haeckel rule. That's why pyridine is an aromatic compound. Here we can see the resonance contributors of pyridine. Nitrogen, due to its electronegativity, withdraw the pi electron, and due to the delocalization of the pi electron inside the ring, pyridine forms different contributors like this. Now about the preparation of pyridine. We can prepare pyridine by passing a mixture of acetylene and hydrogen cyanide through a red hot tube. That is, the temperature is very high, around 500 to 600 degree centigrade. And during this reaction, two molecules of acetylene will combine with one molecule of hydrogen cyanide to form pyridine like this. We can also prepare pyridine by dehydrogenation of pyridine with concentrated sulfuric acid at 300 degrees centigrade or with nitrobenzene at 260 degrees centigrade. By another method, we can also prepare pyridine by oxidation of 3-methyl pyridine, which is known as beta picoline, with potassium dichromate and sulfuric acid, which gives nicotinic acid, which on decarboxylation yields pyridine. At pK 5.2, pyridine behave as a base. As it is behave as a base, it reacts with acid to form a fairly stable salt, pyridinium chloride, like this. Because the lone pair of nitrogen in pyridine is present in a sp2 hybrid orbital, which is not involved in delocalization of pi molecular orbital, and that's why they are available for the formation of a new bond with proton, which was released from the acid. Pyridine is a stronger base than pyrrole. In case of pyridine, the lone pair electron on nitrogen atom is present in a sp2 hybrid orbital, but in case of pyrrole, the lone pair electron on nitrogen is present in p orbital. That's why the basicity of pyrrole is reduced by delocalization of the nitrogen lone pair. But pyridine is considerably weaker base than trimethylamine, because the lone pair of electron in pyridine is present in sp2 hybrid orbital, whereas the lone pair electron on nitrogen in case of triethylamine is present in sp3 hybrid orbital. sp2 hybrid orbitals are smaller than the sp3 hybrid orbital. That's why the lone pair of electron on nitrogen in pyridine is more closely associated with the nitrogen nucleus, and that's why they are less available for the formation of a new bond with proton. That's why pyridine is weaker base than trimethylamine. Pyridine is an aromatic compound. We know that aromatic compound usually undergoes electrophilic substitution reaction, but pyridine is considerably less reactive than benzene towards electrophilic substitution, because the nitrogen atom in pyridine due to its electronegativity, lowers the electron density around the ring carbon. That's why the usual electrophile can coordinate with the lone pair of electron on nitrogen to form resonance stabilized pyridinium salt rather than attacking the ring. However, pyridine undergoes electrophilic substitution reaction when extremely vigorous reaction conditions are used. When pyridine undergoes electrophilic substitution reaction, in that case, which position is the preferred position for the electrophile? We can see from the structure that there are three positions, that is 2, 3 and 4 position for the attack of electrophile. Because the 6th position is symmetric with the position 2 and 5 position is symmetric position with 3. If the electrophile attack at position 3, in that case it will form 3 resonance form like this during electrophilic substitution reaction. Again, when electrophile attack at position 2, in that case it will form 3 resonance form like this during electrophilic substitution reaction. And when the electrophile attack at position 4, in that case it will also form 3 resonance form like this during electrophilic substitution reaction. We know that the more resonance form, more stable the product, that is, if an electrophile attack at specific position which has more resonance form, in that case that position substituted product will be the major product during electrophilic substitution reaction, that is for the substitution reaction. But in the 3 position they form 3 resonance form, but we can see when electrophile attack at position 2 and 4, we showed here 2 resonance form with a red circle. Here we can see that here the total number of electron on nitrogen is 6. Actually these 2 forms are energetically unfavorable form, that's why we can ignore these 2 form. So after that we can see when electrophile attack at position 3, in that case they form more resonance form, that is 3 resonance form. That's why during electrophilic substitution reaction in case of pyridine, the preferred product will be the 3 substituted product, that is the electrophile will prefer the position 3 for electrophilic substitution reaction. Here I am showing few example of electrophilic substitution reaction of pyridine. If we do nitration of pyridine, in that case the major product will be the 3-nitropyridine. If we do sulfonation, in that case pyridine 3 sulfonic acid will be the major product. If we do bromination, in that case mixture of 2 products will be the major products. One is 3-bromo-pyridine and another is 3,5-dibromo-pyridine due to polyhalogenation of pyridine. But if we do Fidel's-Curve reaction, in that case we will not get Fidel's-Curve's product after electrophilic substitution reaction, because we have to use a Lewis acid in case of Fidel's-Curve reaction. This Lewis acid tie up with the nitrogen of pyridine. That's why Fidel's-Curve reaction will not occur, we will not get the Fidel's-Curve reaction product in case of pyridine. Pyridine usually undergoes nucleophilic substitution reaction. The same electronegativity that makes pyridine unreactive towards electrophilic substitution makes it highly reactive toward nucleophilic substitution reaction. We already discussed it before. When nucleophile attack in pyridine, there are 3 positions, 2, 3 and 4 position. When nucleophile attack at position 2, in that case it forms 3 resonance form like this. And when nucleophile attack at position 4, in that case also it forms 3 resonance form like this. When nucleophile attack at position 3, in that case also it forms 3 resonance form like this. But in case of position 2 and 4, we can see 2 resonance form which is highlighted here. We can see that negative charge is spread over nitrogen. This leads to the enhanced stability of this form. Consequently, the products with substituents at carbon 2 and carbon 4 predominate. But if we compare between position 2 and 4, which position is the preferred position? Actually, if we compare between 2 and 4, in that case, position 2 is the preferred position than position 4, because this more stable resonance form first when nucleophile attack at position 2 compared to position 4, because at position 4 this more stable resonance form not form first. That's why during nucleophilic substitution reaction, nucleophile prefer the position 2 first. But a mixture of two compound will be produced. One is 2 substituted product and another is 4 substituted product. But the percentage of the 2 substituted product will be the major product during nucleophilic substitution reaction. Here I am showing some example of nucleophilic substitution reaction. When pyridine reacts with sodamide in liquid ammonia, in that case nucleophilic substitution will occur and 2-amino-pyridine will be the major product. First, sodamide will be ionized and the amino anion will attack at position 2 of pyridine. After substituting a hydride ion, 2-amino-pyridine will be produced, and the substituted hydride ion will combine with the sodium and will form sodium hydride. And this sodium hydride, after reacting with liquid ammonia, will be converted to sodamide and hydrogen. If pyridine reacts with sodium hydroxide, in that case also nucleophilic substitution reaction will occur, and the product will be the 2-hydroxy pyridine. Its another name is pyridol, which after tautomerism will be converted to 2-pyridone. When pyridine reacts with N-butyl lithium, in that case after nucleophilic substitution reaction, 2-butyl pyridine will be the major product. So pyridine usually undergoes nucleophilic substitution reaction, and an extreme vigorous reaction condition it undergoes electrophilic substitution reaction also. But pyridine also undergoes oxidation reaction in the presence of a strong oxidizing agent like peracetic acid. After oxidation with peracetic acid, pyridine will be converted to pyridine N oxide or pyridine 1 oxide. Pyridine also undergo reduction reaction if a suitable reducing agent is used. When hydrogenation of pyridine occurs, in that case pyridine will be converted to hexahydropyridine after reduction reaction. Now about the synthesis of a pharmaceutically important compound which contain pyridine ring in its structure, that is the synthesis of pyridoxine, that is vitamin B6. We can see from the structure of pyridoxine or vitamin B6, we can see that it contains a pyridine ring in its structure. For the synthesis of vitamin B6, we can follow this synthetic pathway. We have to start the reaction with 1-ethoxypentane 2,4-dione with 2-cyanoacetamide. When these two starting material refluxed in ethanol and piperidine, it will be converted to a compound like this, which after nitration, a nitro group will be introduced at position 5 of this compound, and after that, if this compound will react with phosphorus pentachloride and phosphorus oxychloride at 150 degrees centigrade, in that case the carbonyl group will be replaced by a chloro group, which after hydrogenation the nitro group will be reduced to amino group, and this cyanide group will be converted to this group. After that, if we do nitrogenation reaction, in that case this both amino group will be converted to phenol group, because here the temperature of the reaction mixture is 90 degrees centigrade, which is more than 5 degrees centigrade. We know that if we do nitrogenation and the temperature is more than 5 degrees centigrade, in that case amino group will be converted to phenol group, that is OH group. After that, if we treat the compound with hydrogen bromide and then with silver chloride, in that case this ester group will be free and it will be converted to like this, that is we will get pyridoxine or vitamin B6. We can use this synthetic pathway for the synthesis of pyridoxine, which plays a key role as the coenzyme in transaminases. Now I shall discuss about another heterocyclic compound, that is quinoline. In quinoline, we can see that a 6-member heterocyclic ring is fused with another 6-membered homocyclic ring, and here the hetero atom is nitrogen. We can also see the resonance contributors of quinoline here. Actually, quinoline forms many resonance contributors when the electronegative nitrogen withdraw the pi electrons, and due to the delocalization of the pi electron it forms many resonance contributors, because the delocalization occurs both inside both the rings. That's why it forms many resonance contributors like this. Here I showed some forms, that is resonance forms of quinoline. Now about the preparation of quinoline. We can prepare quinoline by scrub synthesis. In this reaction, a mixture of aniline and glycerol is heated in the presence of sulfuric acid and a mild oxidizing agent, usually nitrobenzene. The reaction is exothermic and tends to become very violent. That's why ferrous sulfate or boric acid is generally added to make the reaction less violent. And after completing this reaction, we will get quinoline. Another method is Friedlander synthesis. In Friedlander synthesis, which involves the condensation of orthoamino benzaldehyde with acetaldehyde in the presence of an alkali, and after completion of this reaction we will get quinoline like this reaction. Quinoline behave as a base at pK 4.94. As it is behave as a base, it reacts with acid to form fairly stable salts. When quinoline react with hydrogen chloride, in that case quinolinium chloride will be the product, which is a salt. Actually, the properties of quinoline and pyridine are almost similar. Quinoline undergoes electrophilic substitution reaction as it is an aromatic compound. If we do nitration of quinoline, in that case 5 nitroquinoline and 8 nitroquinoline will be the major product. Actually, during electrophilic substitution in case of quinoline, the preferred position is 5 and 8. That's why these two products are the major products after electrophilic substitution reaction. Similarly, if we do sulfonation, in that case, quinoline 5 sulfonic acid and quinoline 8 sulfonic acid will be the major product after electrophilic substitution reaction. Like pyridine, quinoline also undergoes nucleophilic aromatic substitution reaction, and during nucleophilic substitution reaction the preferred position is 2. When quinoline react with sodamide in the presence of liquid ammonia, in that case 2-amino-quinoline is the major product. When quinoline reacts with potassium hydroxide, the major product after nucleophilic substitution reaction is 2-hydroxyquinoline. If quinoline reacts with N-butyl lithium, in that case 2-butyl quinoline is the major product. Actually, these three are the example of nucleophilic substitution reaction. Quinoline also undergoes oxidation reaction when a strong oxidizing agent is used. When quinoline oxidized with a strong oxidizing agent like per-acetic acid, in that case after oxidation the product will be quinoline N oxide or quinoline 1 oxide. Quinoline also undergoes reduction reaction. Depending on the reducing agent, the product may vary. If we reduce quinoline with a mild reducing agent, that is a metal acid combination like tin and HCl, in that case the heterocyclic ring will be reduced and the product will be tetrahydroquinoline. If we do hydrogenation of quinoline using hydrogen gas in the presence of a metal catalyst, in that case both the ring of quinoline will be reduced and the product will be decahydroquinoline after reduction. Now about the synthesis of a pharmaceutically important product which contain quinoline ring in its structure. For example, the synthesis of chloroquine. We can see from the structure of chloroquine that it contains a quinoline ring. For the synthesis of chloroquine, we can use this synthetic pathway, and for the synthesis we have to start with two starting material, that is 3-chloroaniline and another is 2-oxosuccinic acid diethyl ester. When these two starting material reacts in acetic acid at 40 degrees centigrade, in that case condensation will occur and one molecule of water will be eliminated from here and it will be converted to a product like this. When this compound is heated at 250 degrees centigrade, in that case a new bond will be formed between these two carbon and this product will be produced. After that this product is heated or treated with potassium hydroxide in ethanol, and after that the temperature, if we maintain the temperature around 260 to 270 degrees centigrade, in that case decarboxylation will occur and carbon dioxide will be eliminated from here and that compound will be converted to a product like this. When this compound is refluxed with phosphorus oxychloride, in that case this carbonyl group will be replaced by a chloro group and this product will be produced. And in the final step, when this product is treated with 4-amino-pentyl diethyl amine, in that case we will get our target product, that is chloroquine. Chloroquine is a synthetic anti-malarial drug, and for the synthesis of this drug we can use this synthetic pathway. That's all for today. If you like my lecture video, then don't forget to click the like button. You can also share this video to your friends and can also put your comments. Lastly, don't forget to subscribe my channel. Your subscription will encourage me to make more lecture video for you all. Thank you.